All right, here's yet another video in our video series of dealing with these different types of force problems. This was the Atwood machine without any friction. Now what I'm going to do is I'm going to go ahead and add some friction into this problem. So if you haven't watched the other video, these are the numbers and the results that we've got. I might just take a quick picture of that so you have it for reference. And then we're going to change some things. So if we put friction on this, we found out in the last video that this thing is going to accelerate to the right for that one and down for this one. So friction will be pulling on this top object backwards. So that's going to affect our equations. So it's not going to affect our equation for the net force on M2, but it is going to affect our net force equation on M1. We're going to have the tension force minus the force of friction. Right? That equation will stay the same. This one will change, but then that will change all of our algebra. So, a new sheet of paper here. So, as I said, M2 is going to stay the same. The net force on M2 is still going to be the force of gravity pulling downward minus this tension force pulling upward on M2. What is going to change for M1 is we're still going to have tension pulling forward, but now we have the force of friction pulling backward on M1. So let me zoom in just a little bit so the numbers are a little bit more in focus and a little easier to see. And then let's see what this algebra looks like. Once again, substituting in what we know, for M2, it's going to be mass times the acceleration is, I'm going to go ahead and just use the number that we calculated for the last problem and see what that looks like. It was 46.06. That is the mass times the acceleration of gravity, which is going to be 4.7 times 9.8 minus the tension. And that's going to be our equation for M2. For M1, again now it's 10.9 times the acceleration is going to be the tension force minus the force of friction is the normal force times the coefficient of friction. So we need a coefficient of friction. So we can just let mu, this is always going to be a decimal. A lot of the numbers we use, once again, it's not an M, that's one of these mu things, like a U with a tail in the front. Somewhere around 0.3, 0.4 is a general kind of static coefficient of friction. This object's already moving, so it might be slightly less than that. So I guess this is a mu k, because we're going to assume that this thing is moving, and then there's some friction on it. Let's go 0.25. So we have a number that we can use, 0.25. So then the force of friction is going to be the normal force times that coefficient of friction. And once again, the normal force is going to equal the force of gravity on this object, right? Because we're assuming that those two things are equal. And so, since we have our mass of 10.9 kilograms on it, and if we multiply that times 9.8, it's 107. So it's going to be 107 times this 0.25. And I'm just going to go ahead and do all of that math. So it was actually 106.82, but if we take that times 0.25, it's 26.7. So let's use the 26.7 newtons for the force of friction. Once again, I took the mass times the acceleration of gravity to get the normal force, and then we multiply that times the coefficient of friction. Right? Our force of friction formula is, force of friction is less than or equal to this mu times the normal force, which once again, all of our problems so far have been on a completely flat surface, so the normal force is equal and opposite of the force of gravity. We'll do an inclined plane problem next in the series that will incline it, and we'll see how that changes. Okay, but in any case, this is what we have so far. So once again, like most of these problems, luckily we have two equations and two unknowns. I can substitute and do some solving. So in this bottom equation, the tension force is 10.9A plus 26.7 newtons. And then I'm going to substitute all of this in for that tension. So we have 4.7A in the first equation equals 46.06 minus 10.9A minus 26.7. We're going to subtract this entire thing, which makes both of those numbers negative. And then it's just a matter of doing some algebra. 15.6A, I'm adding the 10.9A to both sides. And then on the other side, I'm taking the 46.06 and subtracting the 26.7. I get 19.36. And then divide by the 15.6. right, to get the acceleration, 1.24 meters per second squared. And then like all of the other problems, once we have the acceleration, we can start substituting in and calculating things. I guess we can calculate this tension first. Right? We can put the 1.24 meters per second in there, so we're multiplying times 10.9. And then we're going to add the 26.7. And I did the wrong number in the calculator. I don't know why with this series of videos I may have a lot of calculator issues. So it's 10.9 times the acceleration, 1.24. There you go, I got 13.5, give or take. And then I'm going to add 26.7. Somehow last time I hit the multiplication key. Ah, that looks better. So our FT, our tension force, is 40.2 newtons. So let's kind of zoom back out a little bit so we can see a little bit more of the what's going on. So one more time, I just used this equation, put that in for A, did a little algebra, and got the tension force is 40.2. And then once we know that the tension force is 40.2, then we have two things. We have the net force on M1. So that's the 40.2 tension going this way, and the force of friction of the 26.7 going backwards. So we're going to be subtracting these two, right? Because that's what it says there, the tension force minus the force of friction. So it's 40.2 minus 26.7. And that gives us 13.5 newtons. Which should also be the acceleration times the mass. So if you take the acceleration, the 1.24, times the mass of 10.9, let me just check that out quick. We should actually end up getting something pretty close to this same number. And still, Zaug has calculator issues. 10.9 times 1.24 equals, it says 13.52, which is pretty close to 13.5. The net force on M2 equals, right, force of gravity minus the force of tension. The force of gravity on M2 is the 46.06. And if we subtract the 40.2, yay, 5.9. I can do math right the first time. It's 5.9 newtons, which should also be its mass, which is 4.7, times the acceleration, which is the 1.24, and I get times 4.7, 5.82, which is pretty close to 5.9. Once again, depending upon the sig figs, that's about as close as it will probably turn out. So we have the net forces and the tension force and the acceleration. These are basically all the calculations we would possibly need on this Atwood machine. So this is the Atwood machine with friction. All it does is add the one term into the equation. Otherwise, the equations are the same as the other one. So we have a couple of more videos, one for the inclined plane and one for the inclined plane with friction. Thanks for watching.